Bismillah ar-Rahman ar-Rahim. So today we are continuing with the 0625 March 2023 paper 42. And just as we begin, I'm going to go back a few questions to this one, right? And we actually left this because there was a slight confusion. And the confusion was to get the direction relative to the riverbank. And the formula is tan theta equals to Fy over Fx. And what we were trying to do, was 2.5 over 3.5, and then taking a tan inverse, and whatever angle we were getting was wrong. And the reason for that, right, is that the tan theta in this case, if I just sort of erase the blue lines, or most of it, in fact,
Yeah.
gotten a bit messy. Try to redo this a bit. And so this is the riverbank, right, RB. And this is your ship. It's moving at 3.5 meter per second. And this is the, right, so this is your ship or boat or whatever it is. And it's and the current, right, is 2.5 meter per second. So this is how the ship will end up moving, right? And its speed will be 4.3 meter per second as we've calculated. Now, as for the angle, right, if this is what we're calculating as theta, then this is the angle of movement of the ship relative to its own original movement, which is perpendicular to the riverbank. Okay, now if I redraw this over here as a square,
Okay.
right, this is the direction of motion, original direction of motion of the ship, right? The boat, it crosses the river. So this is the boat initially crossing. So this is the initial movement, right? This is the current. This is the riverbank, and this is the actual movement of the ship. And they're asking us to find the speed which we have and the direction of the boat relative to the riverbank. So the theta that we need to find is actually this one.
Yeah.
Okay, and in that case, right, we have 2.5 over here, right, and we have 3.5 over here, right? We just take those values, right? This was 2.5, this was 3.5. So, right, it's going to be the same thing in a square. So if I redraw this triangle over here, this is what it's going to look like. Yeah. And in this case, when we try to find tan theta, right, it's Fy over Fx, which will give us 3.5 divided by 2.5. Right, and then you take a tan inverse of that, and you will get the answer that you're supposed to get, right, which is of 54 or 55 degrees when you round it up. So the actual thing that you'll be getting, I just move to the calculator, right, it's 3.5 divided by 2.5, which gives you 1.4.
Yeah.
Right, and so you're taking a tan inverse of 1.4.
Yeah. Okay.
which is giving you 54.46.
54.46. Okay.
Right, so they've accepted 54 and 55 both. Why? Because if you're taking it this directly to one decimal place, right, it's going to round down to 54. If you're going to first convert this to 54.5, and then that 54.5 is going to convert the whole thing to 55, that's 2 steps of rounding up, right? And so 55 is also taken as, right, a valid answer in the mark scheme. So we can go with 54, and so, right, that would be the direction. Okay, does that make sense?
Yes.
Okay, now let's carry on to where we were, and again, like we did with chemistry, right, hopefully we can speed through this. Okay, question 5. Figure 5.1 shows a semicircular transparent plastic block. A ray of light is incident normally on the curved surface of the block. The refractive index of the plastic is 1.5, right? So calculate the critical angle of the plastic, right? So you're given the refractive index, which is C, right? Do you remember the formula for refractive index in terms of critical angle?
Right.
Right, normally the critical angle is sine I over sine r, but that's not for critical angles. What is the formula for critical angle, the refractive index, when we are using the critical angle?
Is it sin C? Wait, no, it's N first. Okay.
Haram?
I actually forgot the formula.
Hmm?
I actually forgot the formula.
So
1
over sine c,
Yeah.
right? And so what you need is the critical angle. So sine c is 1 over n, and c is sine inverse of 1 over n. And so we do the math, it's 1 divided by 1.5, right? Which will give us how much?
Wait, what was it? 1.5 divided by?
No, 1 divided by 1.5.
Okay. 0.067 in the end.
Right, so it's a recurring, right? 0.66666.
Yeah.
Right, and so without without rounding it off, right, because that is not the, so remember one thing, do not round it off until you get your desired answer, right? So you're not going to use 0.67, you're going to use 0.6666 on the calculator, and then you take a sine inverse of your answer on your calculator. And what is the angle you're getting?
So we're gonna take sin, right? Okay. We're gonna do
Sine inverse. Sine inverse of 1 over 1.5.
Is it 0.618?
No, it should be 41.8, which we can take as 42 degrees.
Okay.
Okay, next, draw the path of the ray in the block, and after the ray emerges from the block.
Okay.
Okay, so now how like you're supposed to draw it over. Now again, looking at the ray of light is incident normally. What does normally mean over here?
It's normal, not abnormal.
No, right? It means that it is perpendicular to the surface at this point, right? The normal is a line that is perpendicular to the reflecting or refracting surface. That means, and remember, refraction does not happen when the incident ray is coming in at 90 degrees, when it's perpendicular to the surface. There's no, it just passes straight through. Okay.
Yeah.
And so you're going to put a ruler over here. I'm going to sort of just try to wing it, right? But you're going to put a ruler over here and draw a line that continues straight into the plastic. Right?
Mm-hmm.
So again, I'm maybe better if I zoom in. Okay. Right, and I will draw that straight. Now, because it is at the critical angle, which means, right, you're going to have total internal reflection. And so
Yeah.
you need to draw it going back out at the same angle. And for this, you will need a protector. Right, so I'm guessing from the dotted lines that I'm drawing it correctly.
Yeah.
And so you're going to draw the reflected light all the way out like this. Okay.
Okay.
And remember that the normal in this case would be this, and I and R should be equal. Okay. Because the angle of incidence and angle of reflection are always the same. So what's happening over here is total internal reflection, and because it came in perpendicular to the surface, it's also exiting perpendicular to the surface, and so you're not noticing any refraction happening right on the curved edge. Okay, so figure 5.2 is a full-scale diagram of a lens and an object. Determine the point marked F. Sorry, what the point marked F shows the position of the principal focus of the lens. Okay. Determine the focal length of the lens, right? So you need to measure that with a ruler. Okay. And since I don't have that option over here, right, I'll just give that to you, and that's 7.2 centimeters. So this is something you need to have a proper ruler for, and then you measure it off the ruler. So that's 7.2 centimeters. That's the focal length, right? The focal length is the distance between the optical center and the principal focus. On figure 5.2, draw two ray diagrams from the object to locate the image, right? Label the image I. So one thing we can take from this, because the object is placed closer to the lens within the principal focus, you're going to get a virtual image. Okay, that's what we believe. So let's see what happens. So the first ray is going to be from the top of the object through the center, like that.
Yeah.
Right, now what you need to do, obviously, if that's the principal focus, the second ray is supposed to go from the top of the object horizontally to the lens. Okay, and then you need to make it go through, so the principal focus, so you need to mark the principal focus 7.2 centimeters on this side as well. Right, so I'm guessing somewhere over here maybe. Right, let's see if that's diverging. It should be diverging. And so you draw that, and yes, you can see that your lines, your rays are not converging. Okay. Are you following?
Yes.
Are you sure?
Yes.
Okay, so you can see that you're not going to have converging lines, and therefore you're not going to have a real image. And so what you need to do now is you need to trace back these lines with a dotted line. Again, I don't have the dotted line option in this free to use version. Right, so I'm going to do try and do it like this, see how it works. Right, extend it as far back as possible, and then take the line from here and extend that back as far back as possible. And if I'm doing this correctly, that's where it is forming an image. Again, so somewhere over there. Okay, should be something. Again, this is not accurate. This is not what you would actually get in your exam. So you'll be using a ruler. It will be obviously more accurate as compared to what I'm doing, but that's what you should be doing, right? And so your object is going to be, again, if I take, right, I'll just use the same. So if you take this point, I zoom in a bit, and we take the point, you'll be drawing a line like that. You'll be drawing the arrowhead, and you'll measure this, and that will be your image.
Yes. Okay.
It used to give,
You seem proud of your drawing.
yeah,
You seem proud of your drawing.
it seems what?
You seem proud of your drawing.
No, I was adjusting the zoom.
Yeah.
I was adjusting the zoom. Okay. Oh, look, the human eye.
More looks like a ball.
Well, it is. Okay, they haven't asked for the image, right? So label it eye. So there you go. You label it eye. Okay. Figure 5.3 shows a simplified diagram of an eye with rays from a distant object and the path of the rays inside the eye of a person with short sight. Right? And figure 5.4, on figure 5.4, draw an additional lens outside the eye to correct the short-sightedness and show the path of the rays inside the eye. What kind of lens are you going to use?
Concave?
Concave, right? So that's also called a diverging lens.
Yeah.
Right? And so you're going to use that. Or in fact, sorry. You got a diverging lens. And so the rays are, I'm going to be crude with this. The rays are coming in and they will diverge. I need to reposition the lower one. Right, obviously you're going to draw this much neater. So they're going to diverge, and then right from here you're going to draw them converging on the retina. Okay.
Yeah.
All right, question 6. Question 5 took a bit of time. Question 6. Sound waves have compressions and rarefactions, right? So it's a longitudinal wave. Explain what is meant by compression and rarefaction. So that is from memory. I'll, leave that. Let's move on. We can see light from the sun, but we cannot hear the sound from it. State the reason for this, right? So sound needs a material medium, and there's vacuum in space, so you can't hear it. During a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is heard 9 seconds after lightning is seen. The speed of sound in air is 340 meters per second, right? So distance. So,
Distance versus speed multiplied by time.
yeah, so distance is v into t, which is 340 into 9. So what are we getting?
3060.
Really?
Am I wrong?
Wait, let me check. I haven't done it. That's 340.
Yeah, 3060.
Yeah. So for some reason they've rounded to 3100. I don't get their rounding, right? So it's supposed to be 3060 meters. They've taken it as 3100 meters.
For what reason exactly? There's no point.
I don't get it.
Yeah.
Okay.
Is it important to round?
I mean, rounding, right? But again, right, you're rounding it up to the nearest 100 meters. Have they said that?
I mean, rounding also makes sense if the answer is decimal, you know?
Well, I mean, even decimals, right? Yeah. So if you're doing like 2 significant figures or 3 significant figures, and rounding the decimal is going to give you like a whole number or something, that like, but you're rounding 3060, which is a whole number. Well, it is a whole number, and it is right, and you're doing that to 30. That's not what's making sense to me. I might be
Exactly.
I might be missing something. Okay. In a lightning strike, there is a current of 3 into 10 to the power of 4 amperes for 48 milliseconds. Calculate the charge that flows. Right, so if you remember the formula for current, right, not V equals to IR, because obviously you don't have any voltage and you don't have any resistance over here, right? So current is the flow of charge over time. So that's I equals to Q over T. Right, so Q equals to IT, which is 3.0 into 10 to the power 4 times 48 milliseconds. Right, so 48 milliseconds is 48 into 10 to the power minus 3 seconds. All right, so do the math, please.
Okay.
It's 1440.
Yeah.
Huh?
1440.
1440?
Yeah. We both are getting the same answer.
Do we have to write it in code?
So into yeah. So 1440 coulombs, right? And you put a C over here, because remember, always check if they've given the units or not. In fact, it's always safer, even if, for example, they had a C over here, like they do in some of the questions, right? They put in the unit. Like over here, they put in kilowatt hour, right? And so we didn't bother with the unit. But in others, they don't. So even if they have put in the unit, always put in the unit for yourself. That's the safest thing you can do. Okay. Define potential difference. From memory, I'll leave that. State the equation which defines electromotive force. Right? So That's work done per unit charge. Again, that's from memory. The EMF of a battery is 9 volts. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 coulombs around the circuit, right? So using that formula, and what you need to find is the work done, right? So W equals to E times Q,
Yeah.
right? And so that's 9.0 into 30, right? And so what are you getting out of this?
270.
270.
Yeah.
270 what?
Joules.
Joules, right? Work done and energy are both in joules. Okay, a circuit consists of a DC power supply, a lamp, and a thermistor. Draw a circuit of these components connected in series. Okay, so a DC power supply,
A lamp.
lamp is how?
X.
In a circle.
Yeah.
And what about thermistor?
Square.
Rectangle. But that's for a resistor, so we need something else.
A line.
What kind of line?
Double line.
Like
small
like a hockey stick,
No.
right? That is a thermistor.
Okay.
Okay, explain what happens in the circuit you have drawn in C when the temperature of the thermistor is increased, right? So a thermistor works in the way that it's a temperature dependent resistor, and when the temperature increases, the resistance actually decreases, right? And so we kind of made a mistake over here. The thermistor should be before the lamp. Okay.
Yeah.
And so what would happen as the temperature increases, the resistance of the thermistor will drop, right? And so more current will pass to the lamp and the lamp will be brighter, right?
Yeah.
Okay.
Yeah.
I just realized I'm solving the paper on my own. I'm not really asking you guys to do it.
That's good, nah?
No.
Yes. You know what's Omar's was now? It's a 26 book and 1.6.
Okay. Is this the last question? No. Oh, we still have 3. So 1 question per page. Okay. Figure 8.1 shows a horizontal flat coil in a magnetic field. The coil is connected to a cell. The coil rotates. Determine the direction of movement of side AB relative to the plane of the coil. Right? Tell me.
The direction would be downwards.
How?
Wait.
First of all, yeah, go ahead.
Are we gonna use the hand thing? I don't wait. Fleming's rule.
Fleming's left hand rule, yes. So your index finger is what now?
Downwards.
No, your index finger, what does it?
Magnetic field.
Magnetic field, yeah.
Yes.
Right, so the magnetic field is north to south.
Yeah.
What's the direction of current through A and B?
Yeah.
I'm asking what is the direction of current?
Oh, wait. To the side.
This is the positive terminal. The longer line is always the positive terminal. This is the negative terminal, and so that is the direction of current,
Yeah.
right? And if you hold your left hand in this way, your thumb is going to be pointing downwards, and so direction movement is, you can either say downwards or you can say anti-clockwise. Explain how you determine the direction in A. So everything that we just said, right,
So-
using Fleming's
Who's not instructed?
left hand rule and the current and magnetic field are, I'm sorry, I'm scribbling, are at right angles to each other. Right, and there is a downward force on the coil. Okay.
Okay.
So state and explain what happens to the coil as it reaches the vertical position, right? So when it's over here and vertical, right? AB. This is, yeah. Okay. So what happens to the coil when it reaches the vertical position?
Wait. Karim, you can answer,
So this is basically a setup for the DC motor, right?
Yeah.
So what happens right at the vertical position?
Yeah.
You can either say that the coil stops, right? Because the electric field and the magnetic field are sort of right aligned, and so there's no force. Right, and after that, the coil actually changes direction. Or in fact, instead of saying the coil changing direction, right, we could say that the turning effect right decreases or becomes zero because you said stop. Okay, to operate a motor, a split ring commutator and brushes are added to the part shown in figure 8.1. Explain the effects of the split ring commutator and the brushes on the action of the motor. Right? So what happens? Because if it's connected like this, then it will just reach the vertical position and stop. Right? So what do the slip rings and commutator and brushes help with doing in this setup?
Can you go back to the question?
Could you repeat that, please?
It has been increasing
All right, Sobia.
The provides the brush. Wait, the brushes provide electrical connection.
We're not talking about the battery. We're talking about the split ring and the brush.
Yeah, the brushes.
Yeah.
They provide electrical connection,
Okay.
and the split ring. Honestly, I don't know about the split ring.
Okay. So what's going to happen to the current?
Right. It would be continuous, wouldn't it?
Yeah. So the current is maintained, right? Because of the brushes. And right, it's actually, so it's what, 3 marks, right? And the split rings allow for the current to change direction. Right, and so the current reverses, and that keeps, and so what happens is, this is not right, if you go and check the book and the explanation, right, at that position when the current reverses, it will cause the, right over here, it caused a downward force, then it will cause an upward force, and that will keep the coil rotating anti-clockwise in this case, right?
Yeah.
Okay. A nuclear power station has a reactor where controlled nuclear fission of uranium-235 takes place. Explain what is meant by nuclear fission, right? So it is the breakup of larger nuclei into smaller nuclei. Energy is released, right? Large unstable nuclei, right? The nucleus splits and releases energy and turns into smaller nuclei, right? So that's from memory. Now state one advantage and one disadvantage of generating electrical power in nuclear power stations compared with electrical power generated using wind turbines. Right, you can come up with that answer. Just give me a sec, I'll be back. All right, I'm back. So do you have a response? One advantage and one disadvantage of generating electrical power in nuclear stations as compared to wind turbines.
Advantage might be reliability.
So it does not depend on the weather.
Yes.
Okay, that is a valid response.
Disadvantage, but it is expensive
Could you repeat that?
and requires that it is expensive and requires a large area.
So it is costly. Yes, you can go with that. Okay. So deuterium is an isotope of hydrogen with one proton and one neutron. Nuclear fusion occurs when two nuclei of deuterium combine, an isotope of helium and a neutron are formed. Use nuclide notation to write down the nuclide equation of this reaction. All right, so deuterium would be how? Right, the protons come below and the mass comes up at top.
Yeah.
So you've got two deuteriums, and those are combining to form,
The mass would give us for 2 protons.
right? So you're getting helium with 2 protons. Now,
And
ideally, this would be 4,
Yes.
But what they're saying that a neutron is also released, right? And
Okay.
that is 0 and 1. Now the problem, remember that law of conservation, right? So the total number of nuclides on both sides. So you've got 2 protons over here and 4 neutrons. Over here you're getting 2 protons and 5 neutrons, which does not make sense. You cannot get a neutron out of thin air.
Yeah.
Okay. And so what are you going to do now? A neutron is formed, right? So you have the helium, you have the neutron. You can't like remove the helium, you can't remove the neutron. So how
Yeah.
will you balance it? How will you end up with 4 neutrons over here, not 5?
You gotta put 3 on the helium.
Yes, because it says it's an isotope of helium, right? So there, you can say fine. This is an isotope of helium that has 1 less neutron,
Yes.
and that would be your answer. Okay?
And that's the end of the class.
No, we still have this.
Is that the last question?
Yes, this is the last question.
Okay.
So the time taken for Mars to orbit the Sun is 690 Earth days. The average orbital radius of Mars is 2.28 into 10 to the power 8 kilometers, and Earth day is 24 hours. Right? So calculate the average orbital speed. So again, speed is
2 pi r divided by orbital speed.
yeah. So orbital speed is 2 pi r, right, over time.
Yes.
And so that would be 2 into pi into 2.28 into 10 to the power 8. Now, how are we going to get time?
Mm,
Right?
4 hour?
690 days into 24 hours into 60 minutes into 60 seconds.
Damn.
Okay.
Yeah.
And so because they wanted in kilometers per second, if they wanted in kilometers per hour, we would have stopped at 24 hours.
Yeah.
Right? But they wanted, so why are we converting it all the way to seconds? Because they're asking it for kilometers per second. Right? So these are the finer points that you need to be careful about. You need to keep a watch of. Right? Okay.
Yeah.
Doing the math, I'm just going to skip forward and we're going to get a big number, which is 59,616,000.
Yes. Yes.
Did you do that math?
I multiplied all the denominators. The 290 multiplied by 24 multiplied by 60. So that gives that answer.
Yeah, so that's giving you, sorry, not seconds, kilometers per second.
Wait. Don't you wanna do the numerator as well?
Oh, sorry. This is the seconds in total. So
Yeah.
you divide the numerator obviously, and you're getting 24 kilometers per second.
Yes. Yes.
Okay, so state the shape of the orbits of planets. So we know that they're not round. What is the shape of the orbits?
Sphere?
No, it's called elliptical.
Oh, okay.
Right, they're sort of like ovalish, not exactly round.
So the
Okay,
Earth is not round. It's
the
oval.
orbit
Oh, the way they
move
circle
around
around.
the, yeah.
Okay.
Okay, light from a distant galaxy is red shifted. Explain what is meant by redshift.
Mm, I think, have you done this question before?
It has come up earlier, yes. They asked about redshift. So redshift is when the wavelength appears
Is
to be
increased.
longer, right? A wavelength appears to be longer.
Oh yeah, this question came before as well.
And so it's 2 marks, you need 2 points. And this is a sort of evidence that galaxies are moving away from the Earth and the universe is expanding. Okay. State the quantity that the redshift of a galaxy is used. That the redshift of a galaxy is used to calculate. What quantity is the redshift used to calculate? What do they use the redshift to calculate? Or what do they calculate using the redshift?
Velocity?
Yeah, so velocity of what?
This
I mean, this, according to the mark scheme, this would get you a mark, but I'm asking the velocity of what?
at which Earth is.
So our reference point is Earth, and so the velocity which a galaxy is moving away from Earth.
Okay.
Okay, and that is the end. Congratulations. Right.
Oh
So
wow.
yeah. So some weaker areas did come up. Right. You should highlight them for yourselves, and you should review. There is still some time, so go and revise and review.
Yeah.
Right. And practice as much as you can for whatever time is left. We still have a class tomorrow,
Yeah.
so we'll be going over paper 4, inshallah.
Inshallah.
All right, see you then.
Okay then. Allah Hafiz.
Allah Hafiz.